Okay, so now let's talk about lines and planes in 3D. All right, so let's start with the lines first. Line equation. And it's helpful if you picture line as a trajectory of some moving particle. Okay? So think of it this way. Suppose there is a point particle moving in space, like that. And its trajectory is given by the following formula. X equal to AT plus X naught. Y equals to BT plus Y naught. Z equals to CT plus Z naught. So think about a point particle moving in space whose position at time t is given by this. I put letters, but if you don't like letters, you can just think about numbers here. 1, 2, 3, 4, 5, 6. If that helps you, then think about it that way. So you have some numbers here, and it's really a function of t. So when t is equal to 0, all these will be 0, and you will have x0, y0, z0 as its initial position. That's where this particle is. 1 second later, that's when t is equal to 1. You put 1, 1, 1. You see that this plus that is the x position, x coordinate of that particle. This plus that will be the y position, y coordinate of the particle, and so on and so on. Okay. All right. Now, to understand what kind of motion this is, we can just differentiate everything. Okay. So let's try to differentiate. Let's differentiate with respect to t. So what's dx dt? A, right? We're treating these as functions of t, and you're just treating a and x naught, these as other variables as numbers. Okay, so if you differentiate this, x naught is a constant, so that becomes 0. If you differentiate at, it's just a. What's dy dt? B. dz dt? C. Then you think about the physical meaning of the derivative. What's the physical meaning of the derivative? Okay.
Position?
No, this was the position.
Oh.
If you differentiate the position, you get velocity. You get rate of change of the position, which is called a velocity, right? So this is a velocity. And as you can see, it's a vector. Of course, velocity is a vector. So this is how you can understand this whole picture in terms of position and velocity. So there is something called the position vector, P vector. Position vector, and we're trying to say the position of the moving particle is AT plus X naught, BT plus Y naught, CT plus Z naught. And if you differentiate the position, it gives you velocity, and we're trying to say the velocity is, if you differentiate this, you get A, differentiating this, you get B, differentiating that, you get C. That's what we're getting. Now, let me add a little bit about the position vector. What's a position vector? Well, position vector is a vector which keeps track of a position of a particle, and the way it does it is by whenever you get a value of the position vector, you move it so that the initial point of the position vector is at the origin. Then the terminal point of that position vector is where this particle is at. That's how you understand the position vector. Okay? And of course, if you differentiate the position vector, you get the velocity. If you differentiate the velocity vector, you get acceleration. So what do you get if you differentiate this one more time?
0.
0, 0, 0. Okay. So now let's think about what this means. This means there's no acceleration. It's constant velocity. Now, if you think about this, there's actually a difference between a constant velocity motion and a constant speed motion.
Constant velocity is the absolute?
No. Okay, velocity and speed. Which one is scalar and which one is vector? Velocity is a vector and speed is scalar, right? Okay, can you give me an example of a constant speed vector, a constant speed motion which is not a constant velocity motion? What's the difference between saying constant velocity and constant speed? Yeah?
Velocity, constant velocity is in the same direction.
Uh-huh.
And constant speed is just the same.
It doesn't
speed in
have
different
to be
direction.
the same direction. Speed could change. So one example is a circular motion. The Earth, well, it's almost a circle, but it's really an ellipse. But if you think about these motions where it's going circles with constant speed, that's a constant speed motion which is not a constant velocity motion. Okay. So what do we have? Which do we have? Do we have a constant speed motion or a constant velocity motion? This is a constant velocity motion because not only its magnitude is not changing, the direction is not changing. It's always this A comma B comma C. It's fixed direction. It's moving in a fixed direction. Therefore, what can we say about its trajectory? What kind of trajectory could it be if it's never changing its direction?
Straight line.
It should be a straight line. Okay. Got that? Okay. So, with this consideration, you can go back and say that the trajectory of this equation is a line. So we will actually say that this is a line equation in 3D. And this is in parametric form. You may never heard about what parametric form is. Parametric form is it's involving t. Okay, that's what parametric form is. Now, this does look a lot different from what you're used to in 2D, right? So to give you an idea of why this is a line equation, let's go down to 2D and see what it does. So I'll now speak with actual examples. So in 2D, all you need to do is to get rid of z, right? Then we have a 2D whose trajectory is a straight line. And let's see what that gives us. So suppose I have x equals to 1 times t plus 2 and y equals to 3t plus 4. I just pick these numbers randomly. So just you can put anything, just 4 numbers just like this. Okay? And I claim that this parametric equation gives us a line. And our goal is to actually change this into a form that we recognize. I mean, this is not the usual line equation that we recognize. So let's try to change this into a line equation form that we recognize. Okay? And it goes like this. When you're given an equation in parametric form, the way you unparametrize it, in other words, the way you get rid of the t to get a relationship between x and y only, is done by the following way. You solve for t for one of the equation, and if you have t equal to something, you plug that back into the next equation, and then t is gone. Okay? And you get some equation. Let's see what that gives us. Okay? So let's see. This one is x equals to t plus 2. That's what it means. And therefore, if you solve for t, t is equal to x minus 2. Right? Now you plug that back in here, so you get y equals to 3 times x minus 2 plus 4. T is replaced by x minus 2 because that's what t is equal to. Right? And then we can further solve it and say y equals to 3x minus 6 plus 4 So we get y equals to 3x minus 2. And yeah, this is the usual line equation that we are used to. It has a slope of 3 and y-intercept of -2. We can even draw this comfortably because there's -2 and the slope is 3, so it's more like this. That's the line. That's the trajectory of this equation that we have. Okay. Now the next obvious question is then, why are you doing it like that if it's this easy? Why are you giving me the harder version? Why don't you give me something like this for 3D? Of course, that's the obvious question that you will have, right? So let's go for it. Okay. So we will try to take this and unparametrize it. And by doing it, we will get some insights into the line equation in 3D. Right? So let's try that. All right, so the line equation in 3D. So we do the following. We do the same. We solve for t. Okay, so first AT is, let's solve x naught both sides. So AT is equal to x minus x naught. And then I divide, which gives you t equals to x minus x naught over a. Okay. Now think about what we will end up with. You will plug this in here and there. Then suddenly you realize that if you plug it into the next two and get rid of the t, you don't get a single equation. You get two equations, right? So you immediately realize that something different is happening in 3D. It's not the same as 2D. In fact, this type of equation, if you write in 3D, if you think about this as a three-dimensional equation, this will no longer be a line. Line equations in 3D look completely different than in 2D. To surprise you even more, you will later learn that this equation will rather give you a plane, not a line in 3D. Okay? But I'll explain why later. Okay? All right. So coming back, so you end up with two equations. Now, but because what you're getting is not that pretty, instead of unparametrizing it that way, what people try to do is rather solve for t for everything, and then write down another set of equations that's more symmetric. So let me show you. If you solve this for t, it'll be bt equals to y minus y naught, and then you divide by b, you get t equals to y minus y naught over b. And then if you solve this for z, you get ct equals to z minus z naught, and dividing by c, you get t equals to z minus z naught over c. And think about it this way. All of these are equals to t, right? So shouldn't they be equal to each other, right? Okay. So that's the equation we write. X minus x naught equals to a. X minus x naught over a equals to y minus y naught over b. Okay, and then this is equal to z minus z naught over c. Yes? Is equal to t. Is equal to t. But we don't write t because our goal is to get rid of t. Now this is still really two equations if you think about it, because they're two equal signs, right? So one equation is that the first two is equal to each other. The next equation is that the second two is equal to each other. So in other words, there's no way getting around the fact that if you want line in 3D, you need at least two equations rather than one. So that's something that you have to accept. And now let me add some more details to this. First, the name for this is called a symmetric form. Okay, why is it called symmetric form? Well, obviously, it's more symmetric than trying to plug this into the other ones, right? So that's why it's called symmetric form. Okay? So there are two types of line equations people use in 3D. One is the parametric form. Another one is symmetric form. Okay. Now you have to remember both of them. And in addition to this, you also need to know the meaning of x naught, y naught, z naught. Okay. So first, what's the meaning of x naught, y naught, z naught? It's the original position. You know, it's just the value when t is equal to 0. But let's see. Yeah, I guess we didn't go too deep into parametric form to explain to you that there are actually millions of, actually infinitely many different possible parametrization of the same trajectory. Because if you have a trajectory and you're trying to talk about a point particle moving on that trajectory, you don't really need to start from here or there. Okay? You can pick any point as a starting point, and you actually have two different directions. You can move that way or that way, and you can go double time. The speed could also matter. So there are infinitely many different parametrization to a trajectory. And therefore, rather than saying that x naught, y naught, z naught is the starting point, if we want to break our thoughts from the physical context, we can just say this is just a point on the line. That's a geometric meaning. X naught, y naught, z naught is just a point on the line, which happens to be, if we think about this as a trajectory, which happens to be the initial point where the point particle begins. Okay. All right. What's the meaning of ABC then? It's a vector. In the physical context, it was
Slope.
yeah. That's the geometric one. Okay. Yeah. In the physical context, it was the velocity, right? Velocity, and really what we were interested in was not the magnitude of this velocity, but the direction. Okay. And yes, in 2D we call this slope. Slope gave us the direction of the line, right? However, in 3D you can't really talk about the slope because slantedness could be in many different directions, right? So rather than saying slope, I mean it's kind of like the slope, but never say the word slope in here because that'll be wrong. Okay? It serves as something similar to the slope, but really you have to say direction vector. It gives you the direction of the line. And so an easy question will be something like, given 2 points, find the equation of that line. Okay, so let's try that. Find an equation of the line. Connecting, let's see, 0, -1, 2, and 5, 3, 1. So let's think about this question. You're given these 2 points, and you want to find a line equation connecting the two. Okay, how do we do this? Well, we can choose one of them as a point in the line, right? Okay. And then, how would you get the direction?
Find the vector.
Yeah, if you find a vector between them, it will give you the direction vector that's of the line, right? If you want to go back to that physical picture, this is how you might think. This is the initial starting point of the particle, and 1 second later, you want it to be there. What is ABC? What is x naught, y naught, z naught? You can solve it that way, right? But it's equivalent to what we are about to do. All we want to do is to say solution. We're going to say that x naught, y naught, z naught is this point, 0, -1, 2. We could have chosen this one. It doesn't matter. Okay? Both are right. At the end of the day, it will be the same line. And then we want to say that A, B, C, the direction vector should be terminal minus the initial, so it's 5, 3, 1 minus the initial point, which is 0, -1, 2. And then let's see, this is
5,
5,
negative 1.
comma 4, comma negative 1. 5, 4, negative 1. Okay. And therefore, now we can write down the equation in parametric form. If it doesn't say which, you can either choose to write it in parametric form or the symmetric form, it doesn't matter. If it says symmetric form, then you have to write it in that form. Let's try to write it in both ways. Okay, so the answer is x, y, z. What are the speeds? Speeds are 5, 4, negative 1. So the velocity is 5, 4, negative 1 times t times t times t. And the initial point is 0, negative 1, 2 plus 0, negative 1 plus 2. That will be the parametric form. Or you can write it in the symmetric form, which is x minus x naught, which is 0, over a, which is 5, equals to y minus y naught. Y naught we chose it to be negative 1, so it's minus negative 1, over 4, z minus 2 over negative 1. So both are correct answers. This one is parametric form. This one is the answer in symmetric form.